as an application of the chain rule with the exponential function, we want to sketch the graph of a normal distribution. Normal distributions are central to probability and statistics. We won't need any of that theory here. All we're interested in is a sketching exercise. Now, our graph is going to look like a bell curve. Our function, f of x, is equal to 1 over square root of 2 pi times sigma times e to the minus x minus mu squared over 2 sigma squared. So, our variable is x. Mu and sigma are going to be constants. Now, mu, our mean, if we take all of our x values, we think of our function as assigning a weight to each x value, and then the mean is just going to be the weighted average. Okay, we note our mean is going to be where our critical point occurs. For sigma, the standard deviation, okay, that'll be positive. This is going to measure the spread of the x values. So the precise meaning for that in probability theory, for here, it's just going to be the distance from our inflection points to the mean. Finally, the constant in front. We need this to guarantee that the area under our curve is equal to 1. So that means we'll have a probability distribution. Now, since I'm only interested in sketching, okay, we're not going to worry about the constant in front. I'm going to drop that. So our exercise is going to be to sketch f of x equal to e to the minus x minus mu squared over 2 sigma squared. Now, to sketch the graph, we're interested in items like critical points, inflection points, increasing and decreasing, and concave up and concave down. So for these, we're going to need the first and second derivatives. To take the derivative of e to a function, we need the chain rule with the derivative of the exponential function. So our rule is going to be box is a function of x, then e to the box, if I take its derivative, we get back e to the box times box prime. So for our chain rule, the derivative of e to the x with respect to x is just e to the x. So for our outside function, we just leave it alone, put our inside function back in, and then we just multiply by the derivative of the inside, which would be box prime. So for our first derivative, we're just going to take our function, multiply by the derivative of the exponent. So we rewrite our function, derivative of the exponent, we use the chain rule. So I drop the 2, the exponent goes to 1, derivative of the inside is equal to 1, so I get minus 2 x minus mu over 2 sigma squared. Now, if I'm interested in increasing and decreasing, first I want to find the critical points. That's where the derivative is 0 or does not exist. Here, we're always going to have a derivative, so that's not an issue. So I need to look where it's equal to 0. Now, for our derivative, the part with the exponential, okay, the exponential of anything is always a positive number. So it'll have no effect when we're looking for where the function is equal to 0. It'll have no effect on the inequalities when we look for greater than or less than 0. So we can just drop it. So for our critical points, I'm only looking for where minus mu minus x over sigma squared is 0, or x is equal to mu. So we have only one critical point at our mean. Now, if we put our mean back into the original function here, we'll have e to the 0. So we're going to have at the mean, the value of our function is 1. And just note, if we put the scalar back in, we'll have this value here. Now, if I want increasing and decreasing, same idea. We can drop the exponential. We take this item, and then for increasing, we would set it greater than 0. So I would have, taking out the 2 and the 2 sigma squared, minus x minus mu, which is mu minus x is greater than 0, or x less than mu. So I'm increasing when we're to the left of the mean. If we look at the graph, well, if I'm to the left of the mean, we're over here, coming in, and we're increasing the whole way. To sum up, we have a critical point in our mean. So there we have a horizontal tangent line, On the left, we're increasing. On the right, we're decreasing. So, same computation, just change the direction of the inequality. Now, for concave up, concave down inflection points, we need the second derivative. So we'll take our first derivative, clean up the term that's not in the exponential. So I'll put in the minus sign and then cancel the 2's. We apply the product rule. So derivative of the exponential we've already done, we leave it as is, multiply by derivative of the exponent. So this is the derivative of the exponent here, so I'm just going to square that term. Then we leave this term alone, multiply by derivative of this part. So I'll have minus 1 over sigma squared. We combine things. Okay, we're going to have exponential part times this function here. Now, if we're interested in concave up, concave down inflection points, we don't need to consider the exponential in front. That's always going to be positive, so it'll have no effect on equalities or inequalities. Now, we want to know where our second derivative is 0, so that'll give us potential inflection points. Set this equal to 0. I have mu minus x squared equals sigma squared. Okay, we can flip the x into sigma. I square root both sides. That gives me x minus mu equals plus minus sigma. Okay, we have two solutions. So push the mu to the other side, and then our potential inflection points are at mu plus minus sigma. So I mark them off in our box for concave up and concave down. Now here, instead of manipulating the inequality, I'm just going to check a point in each region to determine concave up or concave down. I check x equal to mu. Okay, I only need to put it in this part here. That's going to give me minus sigma squared over sigma to the 4th. That's definitely negative. So we have concave down here. To get points that are in the outer regions, I'll use mu plus minus 2 sigma. So mu plus 2 sigma would be over here. Mu minus 2 sigma will be over here. When we put them in to our function, we get 3 sigma squared over sigma to the 4, and that's definitely positive. So we'll have concave up in the outer regions. Now, for the points where the second derivative is 0, we have inflection points. There we have concave up to concave down to concave up. So we have a switching concavity, second derivative is equal to 0 at both points, and the tangent line exists at both points.